Hello guys, I am Dr. Devendra Mishra, working as Assistant Professor in Chemistry at Bidla Institute of Applied Sciences, right? Also running this Tetrahedron Chemistry Classes channel, and here are the links available to approach me. Hello friends, welcome back to the Tetrahedron Chemistry Classes. So guys, in today's class I am going to take a very short video about the phosphorescence, okay? And this phenomenon of phosphorescence is very common. It's a very important actually analytical tool. So I'll discuss that aspect with special reference to your coordination compounds today. Okay guys, and see, before starting the video I want to tell you something guys. See, whenever if you find some error in my video lecture, okay, so instead of commenting on the comment box, first you should check actually my description box, because after shooting a video actually I generally goes through my video completely, and if some error I found actually in my video, I made actually those correction in the description box, okay, and as well as I have pinned the comment I have also pinned the comment about that actually error, okay. So it is very important, if you are watching my lecture, then you should first go to the in the description box whether I have written something or not, okay. See, this is something very important, right? So guys, the phosphorescence, you see, this is the picture, and you know this picture actually, this diagram actually is your Jablonski diagram, though it's not a completely Jablonski diagram, it's only a fraction of this one. And these Jablonski diagrams are very important in understanding the phosphorescence and the fluorescence phenomenon, okay guys. So first of all, you see, this is actually the picture here, and say this is the ground state. Forget about the ground state terms and all these things. Say this is the ground state and you have the electrons here. So what will happen when, say, some electron, say for example this electron is here, for example, okay, and if you shine light on this, right, or if you supply energy to this electron, so it will promote it to the excited state, okay. So there may be the different excited state. Say this one is the, say, first excited state. So first excited state, and this excited, see, ground state is the singlet one. You know there are two types of the state based on the your spin multiplicity. So if your ground state is singlet, then your excited state is here also a singlet one, and this is the second excited state. It is also the your singlet excited state. So S represents the singlet one here, okay, and S1 is the first excited state and S2 is the second excited state, okay. So there may be the third, fourth, and many more, okay, but before going into the detail of this, you should focus on this particular one, right? Say if your electron is promoted to the first excited state, since excited state are unstable state, so after spending a few time here actually, right, so this electron will actually fall down to the ground state, okay. So when it fall down to the ground state, then it will emit some radiations, and these radiations actually falls in the visible region of the light, okay. So when it forms in the visible region, it appears a certain color, and that process is known as the fluorescence process. F represents the fluorescence process, and this fluorescence is generally occurred due to the MLCT transitions, right, metal to ligand charge transfer complexes, right, where in that case you will find these MLCT types of the transition. So this may be a very important question for your upcoming NET examination. See which type of the complexes which actually gives the fluorescence. So you will tell the complexes which actually shows the metal to ligand charge transfer complex, this show the fluorescence. But the important thing is that in the fluorescence, the excited state is also singlet and the ground state is also the singlet, okay. So this question actually CSI and NET haven't asked earlier, so there may be a chance they may ask something about this, okay. Then see, you can see here, then what happened in some cases, right, here what I have explained, the electron actually moves from ground state to the excited state and falls back to the ground state and emits certain radiations. But sometimes it also happens this electron actually will not fall back to the ground state, but actually it goes to the different excited state, and that excited is the triplet excited state, okay. So when your singlet excited state converts into the, or electron jumps into the your triplet state, singlet to triplet, this is known as the inter-system crossing, because your singlet system is now converting into the triplet system. Okay, so this is known as the inter-system crossing. And see, first electron will come here actually in the excited triplet state, and from this triplet state it falls back to the ground state. Then this process, in this process it will also emit certain radiation. Then this process is known as the phosphorescence. Okay, and most commonly known as the red phosphorescence, right? So if you see here, what is the main difference here? In the fluorescence, you see the spin multiplicity is the same. If this is the singlet, this is also the singlet. So your fluorescence is actually your spin allowed transition, while in case you can see here, this is the triplet state. Okay, and this is ground state, say it is the singlet state. So when the excitation, when the actually radiation emits from due to this transition which takes place from the excited state to the triplet excited state to the singlet ground state, then this is known as the phosphorescence. But remember one thing, in both the cases, whether it is fluorescence or the phosphorescence, your transition which is actually giving the color to the substance is actually from the excited state to the ground state. This you should remember. Okay, and first of all you should know this actually fluorescence is a very short time process. It actually completes in the 10 into 10 is the power minus 5 seconds. Okay, so and here this phosphorescence is the delayed process. So what is the meaning of the delayed process? So I'm writing here. Say it's a delayed process. Delayed process means it actually takes time more than this particular second. Okay, this 10 is the power minus 5 second. So this fluorescence completes at 10 is the power minus 5 seconds, while this take more than 10 is the power minus 5 seconds. And the important thing is that, see, if you actually remove the source of the radiation, right, whatever the energy you are supplying to the electronic system, if you remove that actually source, then your fluorescence immediately quenches. That means you will not find any kind of the fluorescence if you remove the source. But this phosphorescence is delayed process. If you remove the source of the radiation which you are actually which is used to supply energy to the electronic system, if that source is removed, even then your phosphorus may continue for minutes as well as for the hours, actually sometimes for the hours also. So it's a delayed process, and you remove the source, it doesn't matter, it will continue for the minutes, even for the hours also. So this is the little concept of the phosphorescence. Okay, so and this phosphorescence actually which takes place from the triplet to singlet ground state, triplet excited state to the singlet ground state, right? That means it's a spin forbidden transition. This you should remember. Fluorescence is the spin allowed, phosphorescence is the spin forbidden transition. Now you can see here this phosphorescence is the spin forbidden emission transitions in the visible range. Okay, and generally the complexes which have the D3 and the D6 system, and D6 the lowest spin, not the high spin but the D6 low spin. Okay, they show the phosphorescence, and these are the complexes actually. See, chromium complexes are very common which shows the phosphorescence. So I have given you some of the complexes here. This particular chromium complex actually shows the red phosphorescence, and this ruthenium complex was the shows the bright orange phosphorescence. And you say ruby, you know about the gemstones and like your spinels actually, right? So in this gem ruby also there is certain concentration of the chromium ion. So gem ruby actually shows the colors, and this color is actually due to the phosphorescence. Similarly, this iron complex also shows the phosphorescence. So these are the some complexes which are very common which shows the your phosphorescence. Now you can see here in most of the cases you can see here actually the transition is occurring from the 2Eg to 4A2G. Okay, so I'm coming on these terms actually. So this is your excited state. Okay, this is your ground state, and you see here the spin multiplicity is total spin multiplicity is 2. Here multiplicity is 4. So it's a spin forbidden transition. This you should keep in mind. Okay, similarly if you go for this particular one, so again you can see here 6 it is taking place from T2G5 to T2G6. You can also determine the your ground state term for this one, right? This you should remember. Okay, these much you should know. Now see guys, there is a question in a 2016 CSIR net examination, and it's a very straightforward question. If you know this particular concept, so you will take only 5 seconds to answer this particular question. See, complex, this particular complex shows the red phosphorescence. You know, the phosphorescence is actually takes place from the excited state to the ground state, right? So in that case, you see this chromium is in +3 oxidation state. Okay, what is the meaning of the +3 oxidation state? So it will have the 3 electrons, 1, 2, 3. Okay, 3 electrons. So for this electron, you know, the F state would be there. F state would be there, and spin multiplicity would be 4. And this F state actually splits into the 3 different states. First is, you can see A2G, and second, say your T1G, and then you can have your T2G. This actually splits in this manner actually. And you know, this actually phosphorescence takes place from the excited to the ground state. So this is your first excited state, and this is your second excited state. But in the option, then if you see here, first of all, you have to check the whether the spin multiplicity is same or not. Whenever you have the spin multiplicity same in the ground state as well as in the excited state, you will discard that option. So you see the spin multiplicity is same, 4 and 4, so it's a spin allowed transition, and you know the phosphorescence is the spin forbidden transition, so you can quickly remove this particular option. Similarly, you can remove this particular option also, because it is again the spin multiplicity is same. Now you can see here you have two chances, right? First, you see the 2 and 4, this is spin forbidden, this is 4 and 2, this is spin forbidden. So this again you can immediately remove from here. Why? Because this is the ground state, and ground state, see, in the ground state there is no transition, right, for the phosphorescence, because in the phosphorescence excited state will fall back to the ground state actually, right? So this is ground to excited state, this cannot be your answer. Okay, the only thing you left actually with this is your excited state EG, right, and this is your ground state. So this is the ground state, okay, and this is your excited state, which is the triply degenerate state, and it is actually comes from the your intersystem crossing. Only this thing you have to remember. So whenever you have such type of questions in your examination, first you actually check the whether spin forbidden and spin allowed actually. After that, you will check your ground state and the excited state. If certain ground states are there in the options and you are matching that option, then you can go for that option. And if they are not there, then you should know actually this is actually your triply state. This much if you know, then you can solve the question based on this. So this particular concept actually I want to explain here, because there was a question in the 2016 examination. I hope you will find this particular video useful for you. Okay, so if you are liking the explanation, right, subscribe the tetrahedron chemistry classes and do share with your friends also. Okay, and don't forget to like the video. Okay guys, thank you very much.